Now, last week we had this pretest where you were asked to draw free body diagrams for a rock and a crate. The rock was riding on top of the crate and everything was being pushed across the floor at constant velocity. Okay, that's the key. Equilibrium. Now, the surfaces are all rough. The floor is rough, the crate is rough, the rock is rough. And so let's draw the free body diagrams. We always draw the easiest free body diagram first. The object that's touching the fewest other objects. Well, that's the rock. The first force I put on there is always the gravitational force, Earth on the rock. I then ask, are there any magnets in this problem? Not yet. What touches the rock? The crate. Does it push or does it pull? It's not a string, not a rope, not a chain, so it pushes. Whenever one thing pushes on another, there will always be a normal force. There may also be a friction force. Here's the thing. If there's a friction force, there's only one friction force. I've only got one more force in my quiver here. Okay? That friction force can either point to the right, to the left, or it can be zero. Tell your neighbor what I want this friction force to do. Point right, point left, or be zero. Talk to your neighbor. Okay. It's not hard. I want that diagram to scream balance. If I put a friction force to the right, it screams to the right. If I put a friction force to the left, it screams to the left. That won't work. The only thing left is zero. And that's what the friction force is. Now these are rough surfaces. The nooks and crannies of the rock are meshed with the nooks and crannies of the crate. But why is there no friction? Well, let's imagine greasing down the top of the crate and greasing down the bottom of the rock. If I push that crate from rest, if I start it from rest, the rock's going to slip off the back and hit me on the foot, right? If I want to start this up from rest, I'm going to have to hold that rock on top of the crate. I'm going to have to push them both. But once I get them up to constant velocity, I can take my hand away from the rock and the rock will just keep going. That's Newton's first law or Galileo's law. Once a body's in motion, it wants to stay in motion at constant velocity. The nooks and crannies between the rock and the crate are still enmeshed, but they're not pushing on each other because both things want to just keep going at that same speed. They just travel together without either one pushing on the other, okay, in the horizontal direction. Now let's draw a free body diagram for the crate. The first force I put on any diagram is the gravitational force. Then I ask, are there any magnets? No. What touches the crate? Well, the rock. And if the crate pushes up on the rock with a normal force, by third law, the rock will push down on the crate with a normal force. The other thing pushing on the crate is the floor. Whenever one thing pushes on another, there will always be a normal force. There may also be a friction force. In this case, we can hear the scraping between the bottom of the crate and the floor. So we know that it's a kinetic friction. Because this crate is moving at a constant velocity, and I only have one remaining force, the push by the person, it's got to be equal to that friction force. And remember, that's how we found the magnitude of the kinetic friction force last week, is indirectly through the push by the person. Okay, now, in this pretest, careful folks, people lose points on the next midterm here. On this pretest, you were asked to find the third law force companion for each force acting on the rock. Now, on exam situations, what we find over and over again is people doing this. They say, oh, those two are companions, tick mark, tick mark. And if I had asked you, If there's any force pairs on your diagrams, label them, you would get full credit. But in this case, I asked for each force acting on the rock, find the companion. And so you would only get half the points if you did that. To get the rest of the points, you would have to identify the companion to that weight force, which would be the rock pulling on the earth. So you need to carefully read the problem and see which way it's worded to see what's required for full credit. Okay?